last session of the workshop. It's kind of a tradition in Women in Theory that we try to have an industry session. So 6 years ago, when we were at Simon's, we actually had a field trip to Gagan site. So we enjoyed a wonderful free meal and got a little souvenir. I think it was a very nice water bottle. I still have it. But this time, because of COVID, we decided to invite speakers over. Gagan was going to come here, but unfortunately she tested positive a few days ago, but she's so nice that she's doing a remote talk for us. So Gagan heads the market research algorithms in Google Research. And like many of the speakers here, she was a student here and also a speaker in the past. So let's welcome Gagan.
Thank you, Lisa. I hope you guys can hear me. Yeah, hi everyone. My name is Gagan Aggarwal. Thank you, Lisa, for the introduction. I work as a researcher at Google. And thank you, Lisa, Tal, and Shubhangi for inviting me to give this talk. I would have loved to join you guys for this talk in person, but unfortunately had a change of plans. But I'm still happy that I'm able to give this talk remotely. And at any point in the talk, please feel free to stop me and ask questions. So today I'll be talking about auto bidding. Oops. Sorry. Can you still see my slides? No. Okay, you can still see my slides. I do not know what's going on my side. Just give me a second. That's bizarre. Sorry, I'm just gonna restart this. It's behaving a little funny on my side, my slides. So I'm just gonna restart the share in a second. Present view. Yeah, okay, I think that works. So I will put this one here. Okay, so let's hope we can move through these slides. So, today I'm going to talk about auto bidding and auctions. This is based on joint work with Ashwin Kumar Badani Diuru, Aranyak Mehta, Andres Perlroth, and Junyao Zhao.
Gagan, we still don't see the slides. I don't know.
So let's start with the motivation. When you search for something on Google, you see some ads in addition to the search results. For example, here we are seeing ads for the query flowers, and all these ads are selected using an auction.
Can you?
So let's get into that view.
So, Gagan?
For a query here, we have the query running shoes, and we retrieve all the ads that are relevant for the query and run an auction, select 3 ads to show, and also decide ads. If suppose, just to simplify the situation, let's say we were only picking one ad.
Gagan, can you hear me?
A common auction that is used is called the second price auction.
Gagan, can you hear me?
The victory auction, where we rank the ads based on their bid, or typically bid times and times some quality score, and the highest bidder gets the item, and the price they pay is the second highest bid. Right. So that's what one ad auction looks like. Oops, I am getting pinged. This is not from Lisa. Oh, we can't see the slide. Oops. Hold on. Let me just stop the share and restart. Stop the share. Share screen. Window. This one. So are you able to see the slides now?
Yes.
Okay, not sure. My goodness. Oh. Let me go back to my. Okay, great. Thanks, Shipra. I will start from the first slide. Wonderful. So let's go over here. Yeah. So we can go back here. Okay. So this was my title slide. And then this was just an example to show what the ads look like on a search page. And this is the auction view where still trying to find the Zoom window back. Here we go. Okay. So this is the auction view where we ran a query where we ran an auction for the query running shoes, and we picked 4 ads. But in general, let's say for a simplified case, let's say you were running an auction for just one position, you would have run the second price auction, sold it to the highest bidder at the second highest bid. Okay. So let's hope this works. Can you see the next slide? Unfortunately, my Zoom window is showing me nothing at this point, basically. No, I see. Hold on. Okay, can you see the next slide now? Great. Okay, so now let us look at this from the viewpoint of an advertiser. The advertiser is not participating in just a single auction. It usually submits a bid per click for a keyword and participates on all the auctions that are relevant for that keyword. And based on its keyword bid, it is assigned a rank and a price for every auction that it participates in. And across all of these auctions, it gets a certain number, a total number of impressions, clicks, conversions, costs, and so on, right? So that is its view, that I am participating in all of these auctions, and this is my total cost, my total clicks, and so on. And a bidder could have many different goals across this aggregate, right? Sometimes it is quasi-linear. It is trying to maximize value minus cost. But sometimes it could be trying to maximize something else, and it might have some constraints as well. And this is where auto bidding comes in. So consider an advertiser that has a high level goal that they're trying to optimize and some constraints that need to be satisfied. For example, someone might want to maximize clicks while keeping their total spend below $100, right? Or they might be trying to maximize conversions as long as their average cost per conversion is no more than $3, right? Such advertisers can use auto bidding, where a bidding algorithm bids on their behalf into each auction. And that results in a certain number of total clicks, conversions, impressions, cost, etc. And it's the job of the bidding algorithm to maximize their objective function while satisfying their constraints. So this is the aggregate that they get at the end. So auto bidding is increasingly being used in online advertising, and many major advertising platforms offer auto bidding. Here are some examples of auto bidding products from Google. One offers to maximize your clicks within a certain budget, or maximize conversions within budget, or one is it maximizes conversions, but here the constraint is cost per conversion, like an average cost per conversion should be no more than a specified amount. And in addition, there could be a budget constraint, and so on, right? So these are real world examples of products which offer this. So this brings us to the topic of this talk, right? So the rise of auto bidding has given rise to several new research directions. And this is what we want to talk about here. And note that many of these questions are still open and an active area of research. And we'll talk about some of these challenges. So the first challenge we'll talk about is designing algorithms for auto bidding. And we'll talk about equilibria when all the bidders are using auto bidding, or many of the bidders are using auto bidding, whether it exists, how good it is, and so on. And finally, if we have time, we'll also talk about reserve prices, how they behave in the auto bidding setting. So we'll begin with algorithms for auto bidding. Great. Okay, here we go. So this is the problem. So we'll break it down into 2 pieces. So we'll first talk about just the selection problem, and then in some sense we'll talk about the bidding problem, bidding into an auction problem. So first we'll consider the problem without its game theoretic aspects. We won't consider the other bidders at all. So we'll assume that we are showing only one ad per query, and we'll refer to each query as an item. We will assume that the item costs are fixed. And in practice, as we'll see later, these item costs are actually determined by the bids of the other buyers. And we will assume for the bidding algorithm development that the bids of the other bidders are fixed. So that's how the costs of each item is fixed. And we'll consider two problems. First is the problem of maximizing conversions within budget, B. And the second is maximizing conversions under the average cost constraint. So that's what we'll begin with. So let's see the budget constraint. As you can imagine, this is like a knapsack problem, right? You have a knapsack of size B, which is the budget, and you have items who have some value and have some cost, and you're trying to fill your knapsack with the items which fit within the budget, but which have the maximum value. And in this case, you can do greedy selection by bang per buck. And that will be optimal as long as you're willing to take the last item fractionally, right? And in these settings, each item is typically very small compared to what the bidder is going to get in aggregate. So we don't worry about the fact that the last item is fractional. We can take it, we cannot take it. It doesn't really matter in practice. So we won't worry about the fractional, the fact that we pick the last item fractionally. So so that's our algorithm. We'll just do greedy bang per buck for this case, right? That's our selection algorithm. Now let's consider the TCPA constraint. In this case, instead of having a knapsack of size B, we have the same items, but in this case, we are looking for an average cost constraint, average cost per conversion constraint, that it should not exceed some pre-specified amount TCPA, which is specified by the advertiser. Okay. And in this case, also actually the same greedy bang per buck algorithm works for a slightly different reason, and I leave that as an exercise. So in both of these cases, what we ended up with was the following algorithm. We'll come up with some threshold tau, and it will be optimal to take all items whose cost per conversion is less than tau, not take any items whose cost per conversion is greater than tau. And as I said, like there could be a few items, in this case, one item whose cost per conversion will be equal to tau for input in general position, of course, and we won't worry about these items. Okay. So let's convert this into a bidding formula now. So as we noted in the last slide, with item costs fixed, it is optimal to win the items whose cost is less than tau times the conversions from the item, right? Because we wanted the cost per conversion to be less than tau, which is the same thing. So now if a seller runs a second price auction for each item and the others' bids are fixed, then essentially each item's cost is also fixed. And if we bid exactly this amount, tau times expected conversions for the item, then we'll win. If it's a second price auction, right, we'll win exactly the ones where this quantity exceeds the cost and won't win anything else. And this is what we wanted. So this bidding formula, in some sense, this tau times expected conversions per item is a bidding formula, and this gives us exactly the right selection of items. This works only if the auction is truthful, like second price auction. If the auction is not truthful, in fact, the optimal bidding algorithm is not simple, and there is an incentive to bid differently, like bid less for items where the second highest bid is low. Okay, so let's go to the next slide. Here we talked about two very specific constraints. Now we're going to generalize. So we can get a similar bidding algorithm for actually more complex goals and constraints, many kinds of linear goals and linear constraints using duality theory. And we'll illustrate this technique by considering a buyer who is trying to, again, maximize conversion, but has two constraints now. It has both the budget constraint and the TCPA constraint. And we will write the bidder problem as an integer program, and then we'll relax it, which is the LP that we see on the slide right now. Let me see if you can see my pointer. Can you see my pointer? Okay, sorry, I'm just not able to. I again lost it. Shoot. Oops. Can you guys see my slides still?
Oh.
No. Oh my God. I see. Yeah, I think the moment I touch my computer, it just refuses. It stops sharing. Okay, let me try this again. Share screen, window. And this guy has also. Oh my goodness. Okay. Zoom window, share screen. Okay, I hope you can see this slide now. And can you see my slide now? Yeah. And can you see my pointer on the slide? No? There's a pointer. Cannot see pointer. Cannot see pointer. Okay, that's okay. That's okay. We'll live with this. Okay. So oh, okay, great, wonderful. So here basically we are seeing that we are trying to maximize this conversions. So VI, let's say, is the conversions. VI says how many conversions we get from item I. XI is whether you got the item. So here we're trying to maximize the total conversions. PI, let's say, is the cost of item I, and XI is whether you got the item again. And so this is the total cost. So it's saying maximize my value, keeping my total cost within budget. And this is saying that keeping my total cost below some fixed constant T, which the buyer has specified, times the value. So which is the same as saying that my cost per conversion, average cost per conversion, should be no more than T. So these are the two constraints that we have written. And we can solve this directly, right, and get our XIs. But these XIs will be really hard to use because typically, we have to solve this problem on like historical data, and then we have to use it in the future. So first of all, there is not a one-to-one correspondence between items that arrived yesterday and items that are going to arrive tomorrow. Secondly, this is a huge amount of information to remember, right? So we're going to try and do something better. So we're going to write the dual of this program and then solve this dual, right? And this is actually going to give us something that we can use in practice. So we can prove the following theorem that relates the optimal primal and dual solutions. So what we can show, and this is extending work of Aggarwal, Wang, and Ye in our paper 2 years ago, and what we can show is that let xi star be the optimal primal solution and alpha star beta star be the optimal dual solution. In that case, we can compute this factor, the scaling factor, and only if the scaling factor times vi is greater than pi, whenever this is greater than pi, then xi is 1, then we want to take, in the primal solution, we want to take that item. And if it is less than pi, then we don't want to take the item. This has a very similar form to what we discussed before, right? We had this tau, and we said that we'll take it below tau when the cost per conversion is below tau, and otherwise we want to take it. And this equally easily converts into a bidding algorithm. So we just bid this scaling factor times vi on query I and take the query. And in this case, we'll win the query whenever we need to win it. And as mentioned before, there are, of course, the cases where these two quantities are equal. But what we can show is that for instances in general position, that happens for only 2 of the i's for this particular thing. And again, we won't worry about it. The way you can think about it is that maybe the constraints will get violated by the cost of these two impressions, like at most by the cost of these two impressions, or that you won't be optimal by the value generated by these two impressions. Okay, so a similar technique works for more general constraints, where we can write an LP like this. I won't go into the details here, but we are trying to maximize some value, and we have a cost constraint. This says total cost is less than some budget plus something, and then you can have many such constraints, right? And again, we can take the dual and relate the optimal dual and primal solutions. Let's not look at the theorem, it's grayed out, but it gives us a similar bidding algorithm. And this works in the multi-slot setting as well, where each query doesn't have just one position that we are selling, but multiple positions. And this works for a truthful auction. And again, if we don't have a truthful auction, the bidding algorithm is not simple. I will stop here and see if there are any questions. I cannot see anybody, so if you can basically say something or put in the chat, that would be great. I should not try to do anything. Oh man. Are your speakers on? Yes, my speakers are on. But I am seeing two things, and one of them says is on mute. I'm not sure. The Simons Institute auditorium is not on mute, I think, but the other one might be on mute. And I'm kind of scared to go no questions. Okay. Continue then without hopefully losing my slides connection. Here we go. Okay. So the final question we asked for bidding algorithms is whether this bidding algorithm can be used in practice. We think that it is useful in practice, and I'll point out two nice properties of this algorithm. One is that, as I mentioned before, we only need to remember in the primal solution, right? We need to remember a lot of things. Here, we don't actually need to remember many parameters. We just have to remember this one scaling factor. In slightly more complicated situations, it could be a few parameters. You might have to remember a few parameters, and then we can use this in practice. And then we can apply it basically on a query by query basis. Oops, I should advance my slide. Yeah. And the second thing is, in practice, right? Another question we're interested in is, what do I need to know about the future queries? Because usually you don't have a very good idea of what is going to come in the future. You can try and predict it, but it's not going to be accurate. So how dependent is your solution on that? And from Aggarwal, Wang, and Ye, and Devanur Hayes, etc., what we can show is that if you obtain your alpha star and beta star from solving a dual on a random sample of impressions, then that works pretty well. So if we have a sample of queries which is similarly distributed to what we're going to see in the future, then we can use this. Then the solution that we get is pretty good. All right. How much? I should know this. How much time do I have? Oops. I'm not going to try, and it's going to show me. Okay. I'm sorry. This is. Why does this thing stop as soon as I reach the Zoom window? It just stops moving. No. Oh man. Really not. Okay, let's try this. Oops. I'm gonna get my slides back. I realize that they're probably off by now. So I go to this Zoom window, share screen, new window, this guy, share. Okay, hopefully it's back now. Here we go. And I can see the chat. No questions. Okay, I will go back here. Okay, so next we will look at equilibrium properties under auto bidding. So the question we ask here is that what if all the bidders are using auto bidding? That is, they all have their individual goals and constraints, and they're using the bidding algorithm to produce bids. So then the bids of one bidder depend on the prices that it faces, which in turn depends on the bids of the other auto bidders, right? So the bidders, they keep responding to each other's bids until they settle into an equilibrium. Just to recall, an equilibrium is a setting of bids such that no bidder can improve their utility by unilaterally changing their bid. So the first question is there an equilibrium? And the answer is yes, under some smoothness conditions. I won't go into the proof here. So the next question is, how efficient is this equilibrium? And can we bound the price of anarchy? To answer these questions, we actually need to examine the definition of welfare, because the definition of welfare that we use in the standard setting may not be applicable here. So we'll do that in the next slide. Here we go. Yeah. So for quasi-linear agents, the way we define welfare is the sum over the value that every agent receives, right? So the sum of values that every agent receives. So we can try and do the same thing here. So we can try and define the total welfare achieved by an allocation to be the sum of the objective values that every agent receives. But this may not quite be right, because the objective values might have a very different scale in this case. So somebody might be valuing clicks, somebody might be valuing some very specific actions on their website, and they are not on the same scale. The common scale that we were using earlier was money. And in the quasi-linear setting, the bids that represented the values, they represented the willingness to pay for the bidder, but not in this case, right? In this case, the willingness to pay also comes from the constraint. So the objective value does not tell us how much they are willing to pay. So what we're going to do is we're going to use the cost constraints to infer their willingness to pay, and which is going to inform the welfare of the allocation. So let's see what we're actually going to do. So this was earlier done by Dobzhansky and by Sleme in the context of budget constrained bidders, and their notion is called liquid welfare, and we're going to extend this notion to general cost constraints. So at a high level, we're just going to define the liquid welfare of a buyer as for a particular allocation to be their maximum willingness to pay for that allocation, right? So we can see these constraints here. So their willingness to pay for a particular XI allocation is this amount, taken the minimum over all the constraints. That's their maximum willingness to pay. And that is what we'll call the liquid welfare that this agent achieves. Right? And the total liquid welfare is just the sum over all of these, over all the buyers. So with this definition, we can now talk about how bad is the welfare at equilibrium. For this, we'll use the concept of price of anarchy, which was defined by Koutsoupias and Papadimitriou in 1999. It captures how bad the welfare of the worst equilibrium can be compared to the optimal allocation, right? So for an instance I, you can define opt I as the maximum welfare over all feasible outcomes. So they don't have to be equilibrium, just feasible outcomes. And worst EQ of I is the minimum welfare over all equilibrium. And the price of anarchy is the ratio of opt to worst EQ, the worst over all instances, basically max over all I of opt I divided by worst EQ I. So what one can show is that when everybody is using the bidding formula uh, and they reach an equilibrium, then the price of anarchy is no more than 2. So this is quite nice because it is pretty hard to find equilibrium. Actually, you can show that finding the equilibrium is PPAD hard. So it is very nice that even though the equilibrium is very hard to compute, we can characterize it and say that it's no more than 2. And in practice, it could be much less, of course, like the price of anarchy could be much less in practice. Again, I don't know how much time I have left. I can see the chat stream from the Zoom. Can you? Sorry, can somebody put in the chat stream? If I try to do anything, my slides go off. But I think I can see the chat stream. Okay, 5 minutes. Okay, great. Thanks. That's perfect. So I will make sure. Yes. Okay. So the final question we look at is how do reserve prices behave under auto bidding? Right. So first, let's take a look at reserve prices in the quasi-linear setting to see how they differ in the auto bidding setting, right? So let's assume that a seller is selling several items and they're running a second price auction for each item and a second price auction with reserve for each item, and they're setting a uniform reserve for each of the items. Okay? And we'll see how the change in reserve price affects welfare and revenue here. The first thing we'll note is that a second price auction with reserve is also a truthful auction. So it is in the best interest of each buyer to keep bidding their true value. So when a reserve price changes, the bids actually don't change. And as such, it makes it easier to evaluate different reserve prices and find an optimal reserve price by kind of trying out different prices. Another thing, hold on, my slides are not going. Yeah. So another thing to note is that welfare always goes down as reserve price goes up. This is because as the reserve price is going up, some of the buyers cannot afford some of the queries. And so those might stay unsold, or maybe in this case, since it's uniform reserve price, let's say they just stay unsold. And so the total welfare that is achieved is lower, right? The total welfare goes down. But the revenue can go up and down as reserve price goes up. Okay, so this is what happens in the quasi-linear setting. So let's see what happens in the auto bidding setting. So here again, the seller is selling multiple items, running a second price auction for each item, second price auction with reserve, and the reserve is uniform across the items. Right. So the first interesting difference that happens is that in this case, the bids actually change in response to the change in reserve price, because this is not a truthful setting. So so the reserve price in some sense acts like another bidder's bid, or it has an effect on the cost that a bidder is facing. So let's say I increase the reserve price, their cost might go up, they might have a budget constraint, and they have to lower their bid, right? So the bids change when we change reserve prices and a new equilibrium is reached. As I mentioned before, this equilibrium is hard to compute. And because the bids are changing, it also makes it hard to optimize reserve prices, because if you're trying to try out a new reserve price, you have to let it settle into an equilibrium, or like have to compute the equilibrium, which, as we said, is hard. But another interesting thing that happens is that even welfare can actually go up as you increase the reserve price. So revenue could always go up or down as you increase the reserve price, but now welfare can also go up as reserve price goes up. And I won't have time to show the full example, but here is the example, but I won't go into the details. But the high level idea is that when we don't have a reserve, one of the buyers can save up some money on a query that it was buying. Let's say it was a budget constrained buyer and it saved up some money, and it can use that saved up money to buy a query that it doesn't value very much. and that leads to a loss of welfare because there is a misallocation. Whereas if we had used a reserve price, it would not have been able to save that money on one of the queries that it was winning anyway, and then the second query would have gone to the right person. All right, so I will probably skip this in the interest of time. So I'll conclude by saying that there are lots of new challenges that arise with the increase in auto bidding, opening many exciting new research directions related to bidding algorithms, equilibria, welfare and revenue properties, reserve prices, and auction design. In fact, one of the things we didn't get to was auction design, like what kind of alternate per item auctions can we use and how will they affect welfare and revenue. There's lots of ongoing work here. Another interesting question is about actually designing a truthful mechanism for this setting. So not a per item mechanism, but an overall mechanism that just takes as input these high-level goals and constraints, outputs an aggregate allocation, and does it in a way that incentivizes truth-telling as well as performing well in terms of welfare and revenue. I will conclude here. So thank you all for your attention. I'm happy to take questions if there is time. If somebody can type in the question, that's best, because
That's fine.
Let me actually.
Sensitive to necessity.
I can go back to my Zoom window. Maybe I'll be able to see it better.
So the question is, how do you estimate value
To the LP sensitive.
So the question is, sorry, so the question is, how do you estimate value? I'm so sorry, this is, how to estimate CTR is the solution to LP sensitive to CTR predictions. Yeah, thanks. Yes, so so you can estimate CTR by using historical data. And is it sensitive to, so exactly, so that comes back to the question of, solving it on data which has similar distribution. So it's not super sensitive, let's say, because if you get the CTR wrong by some amount, your final value will be wrong by that amount, but it doesn't. So basically the error in the predictions will likely translate to a similar amount of error in the final value that you receive. Does that answer your question?
Great. Can you hear me?
Yes, I can hear you.
Wow.
Yes, go ahead. I cannot hear you anymore.
Oh, okay. Well,
I can hear you. Yeah, go ahead.
let's thank Gagan again.
Yeah, thank you, everybody. I think I'll disconnect and reconnect because this window is behaving pretty badly.
Very sorry for the technical difficulties, but thanks again.
Sorry, I'm sorry. I'm sure it's on my end, but yeah, I'll see you guys soon again.
Thanks again for giving us a talk, even though you was under the weather. Okay, so let's move on to the next speaker. Now I'm setting up, just have a very quick introduction. You met her yesterday. So Nama currently is a postdoc research at VMware. She'll be moving on to Technion to be a faculty member soon. And before that, she finished her PhD at CMU and won the dissertation award from the CS department. Also a few best paper awards from different conferences. So I guess her stage of career is probably closest to you ladies than any of the other speakers. And I think she was a WIT participant 6 years ago. So.
Okay, good. Right, hopefully the clicker works too. Okay, so thank you for the introduction. My name is Nama Ben David. I saw, I think, all of you yesterday. And so like Lisa said, I'm currently a researcher at VMware, which is why I'm here in the industry session, and I'll be moving to the Technion as an assistant professor next year in 2023. So I just wanted to start by giving a shout out to Women in Theory. So this is actually a picture from our industry session 6 years ago. This is on the Google campus, and this is me over there. So, you know, speaking at Women in Theory means a lot to me. I really enjoyed my time in Women in Theory when I came. And like I told you guys at the panel yesterday, I learned a lot about, you know, being more confident and asking for things. And I think that really helped me in my career. And another thing that I remember from Women in Theory that I really liked is that most of the sessions were technical, which I really appreciated, just listening to a lot of really successful women telling about their work. So I'm happy to contribute to that too. So having said this, this is again my title slide. Today I'll talk about fast and fair lock-free locks. And so my plan for the talk is basically to go through the title in reverse order. So I'll start by talking about what locks are, and then what lock freedom is, and then we'll work our way to fairness and so on. So as promised, I'll start with locks. So the setting here is that we have a machine that has multiple processes. So you can have multiple threads doing things and accessing memory at the same time. And the thing is that, so this is called concurrency, right? Everyone is accessing memory concurrently. And the thing is that setting can get pretty complicated, right? So usually we don't know the relative speeds of the processes. So it could be that one process is executing something and another process comes in the middle and executes something really quickly and so on. So it's kind of a messy setting and it's very hard to reason about. And so to ease the design of concurrent algorithms, locks are generally used. Okay, and in case you didn't take an operating system course or you don't remember operating systems, let me just give a very high level overview of what locks are. So the idea is that I have some primitive called a lock, and it protects a certain part of memory. And then I could have several processes that might want to access this memory. And so to do so, they have to grab the lock. And the idea is that the lock at any point in time has at most one owner. Right, and so if P1 owns the lock right now, then this means that no one else can access the memory that the lock protects. Okay, so P1 now gets exclusive access, and now we can reason about what P1 does just in the normal sequential setting. So, you know, we get this really strong guarantee where you can execute code while holding a lock, and it executes atomically, right? No one else interrupts your work. The problem is that we end up getting bottlenecked by slow processes. Right, so imagine a situation where P1 now owns the lock, but becomes very slow. So it goes to sleep. Maybe the operating system schedules something else on that CPU, so like no progress is being made. And if P2 also wanted to access this lock, it just has to wait, right? And so we're really bottlenecked on whatever slow process now holds the lock. Right, and so to fix this issue, the concept of lock freedom has been introduced. And the idea is, you know, we will design our algorithms so that we will never block on a slow process. And these algorithms end up being very intricate. We have to reason about exactly what interleavings could happen between the different processes. Right, so the downside is that it's very complicated to design these algorithms, right? And it ends up being that you have to redesign each algorithm, especially, you know, for each scenario, right? So it's a lot of work. And so while lock freedom is generally very fast and practical, oftentimes in practice, lock-based algorithms are used because they're just easier to think about. Having said this, lock-based algorithms and lock-free algorithms have been studied a lot in the literature and in practice. And there have been a lot of data structures designed in both settings. And these are just some sample ones that are especially well known. So the exact citations aren't very important, but notice that there are ... on both sides. There are many, many, many papers and algorithms on both sides of this. Yeah, so that's a good question. Yeah, so Michael Scott is actually a researcher in the field. However, this is not just him, it's also someone with the last name Michael. So I always think it's unfair that Michael Scott seems to get the credit and the funny reference, but yeah, so it's a very well-known Q algorithm in the field. Okay, so, but let's recap what these concepts mean, right? So we said that lock-based algorithms, you have a lock where it ensures that some critical code is run atomically, right? And lock freedom, what it really means is that we ensure that no process ever blocks us by being slow, right? And so if you look at their definitions and not just the words that are used to refer to them, you see that they actually don't contradict each other, right? And in fact, so it could be the case that the picture is more like this, and there might be some overlap where we can design algorithms that have locks but guarantee lock freedom. Okay. And so that's the question, you know, can we get simultaneously the simplicity that locks give us and also the guarantees of lock freedom? And you know, from my title, you can already guess that the answer is yes, right? And so what I'll do in this talk is I'll first show you how we design a practical lock-free lock. And then I'll actually talk about an issue that arises, a theoretical issue that arises from our lock-free lock construction where the access to the locks isn't fair, and we'll see how to fix that. And I'll just say that this background picture is supposed to be a flock of birds because we implemented a library for lock-free locks, and we actually called it Flock. So that's the story for the background picture. Okay. So, right, so we want to have locks that also give us this lock-free property that processes don't block. Okay, so, you know, there's a very simple idea that kind of comes to mind, which is that if we have a process, right, and it wants to grab the lock, what it'll do is first create a descriptor where it just basically writes down the code that it would like to run while holding the lock. And it has a pointer from the lock to the descriptor. And once it does that, it can now grab the lock. And so if I have another process come in, now P2 wants to grab the lock. What it can do is it can actually run P1's code for it, right? And so if P2 wants the lock and it sees that P1 is being slow and it doesn't want to wait, it can just do the work for P1 and then it can release the lock itself and put in its own code. So that's a very high level idea of how we're going to achieve this lock-free property, right? I don't have to wait for someone slow. I can just do their work for them. They still get their work done, right? And I'm happy because I didn't have to wait. Okay, so this is the high level idea. There is a problem here though, which is that it's possible that we'll have several processes running the same code at the same time, right? So it's possible that P2 thought that P1 was slow, but actually P1 was actively running the code, right? And so now both P1 and P2 ran the code, right? And we might think maybe that's not so bad. But imagine that the code was just an increment of a value. Okay, so let's say that we have our variable var and its initial value was 0, right? If I have both P1 and P2 run the code, then at the end of the day, suddenly the variable's value is 2, where maybe in my code, the variable's value should never have gotten that high, right? So we could get into a state that was illegal originally, right? So we need to fix this. And so this is the main technical challenge for designing lock-free locks. So the idea of how to fix it is that, well, we want to design code that when we run it several times, it actually doesn't change the outcome, right? So it looks as if we only ran it once. And this is called idempotence. And you might have heard of the word idempotence from linear algebra, right? So if you think in linear algebra, if a matrix is idempotence, it means that multiplying it by itself several times just yields the same matrix. And in our context, it means that an operator applied several times is like we only applied it once. Okay. So this is the effect that we want, except with concurrent code. And I'll just mention that the concept of designing lock-free locks and needing idempotence was actually proposed in the early 90s, simultaneously by Turek et al. And Barnes. But their construction was impractical. So they basically showed how to take some code, not all code, but some classes of code, and convert it into an idempotent piece of code. But it was so slow that it was never implemented or considered anything that we could really do in practice. So our main contribution is to show how to construct idempotent code. So give me any piece of code and I'll convert it into an idempotent piece of code that has the same effect in a way that isn't too inefficient. Okay, so I'll just briefly outline how we do this. The idea is that with our descriptor, we'll not only have our code, but also a log. Okay. And what we'll do is that every time I read the shared memory, I'll log the value that I saw. Okay, so the log will have a number of slots corresponding to the number of reads that I have in my code. So if I want to increment a value, right, I want to read that value and then write that value plus 1. I'll initialize my log with some like null value. And then when I read, I'll go to the variable, see that the value is 5 and write it into the log. Okay, and now after I did that, process P1 can go ahead and write the new value into the variable. Okay. Now later, if another process, the orange process P2 comes in and it reads the value, it can go and it can see a 6. But then when it goes to the log, it sees that the value is not null, but actually something else. Right. So now instead of reading the value 6, it will adopt the value in the log. Okay, and so now P2, even though the value on actual memory has changed, it will read the original value. Okay, and so now P2, when it moves on and writes the value plus 1, it will write the same thing that P1 did. Okay, so this is the idea. We log all the reads so that all the reads return the same value for everyone. Okay, and the concept here is really if we have some code that's deterministic and everyone starts in the same state, and all of their reads return the same value, then this means that all of their writes will do the same as well. Okay, yeah.
Sorry, can you just explain this? So if I see the log doesn't match memory, like why I should just stop at that point?
Yeah, so that's a great question. It's so the different speeds of the processes could actually change over time. So it could be that P1 was fast at the beginning, was faster than P2, but maybe stopped right before or right after this, right? So in this case, there's only like, okay, I read and I write, and P2 sees that it was written and we're done. But it's possible that there's like a bunch more code to do, and maybe P1 stopped in the middle, right? Which is why we want to continue. But good question. Okay, so this is the high level idea. Yeah.
So what all information do you need in your log? Do you only need, like, I'm wondering how P1 and P2, what information tells P1 and P2 that they're executing the same piece of code? Like, it seems like just having the history of what the variable was, like, it's enough.
Right, so notice that in our descriptor, right, the log and the piece of code that you're running are associated together. Right, so if you're helping someone else and you're running a different piece of code, you have a different log, right? So that's why we know sort of by default that if you're accessing this log, it's referring to the same piece of code. Good question. Okay, so this is the high level idea. And so what we show in our paper is that, you can give me any piece of code. If it's written with just reads and writes, then I can convert it into an idempotent piece of code that has the same effect as the original code. And I add just constant overhead, right? So the overhead is now I'm accessing the log on every instruction instead of just accessing the memory, right? And in fact, in our paper, the result was a bit more general. So you could do not just reads and writes, but you can also have compare and swaps, which are atomically allow you to do a little bit more. And you can also have allocations and releases so you can manage your memory. Okay, but this is the high level idea. And so now I'll just very briefly show you some experimental results. I know this is a theory audience, but I promise it'll be quick. So like I said, we built this library for lock-free locks called Flock, where you can basically take a lock and replace it with a lock-free version. And we show that using this library, it's actually very easy to implement lock-free algorithms, right? So generally lock-free algorithms, there are entire papers that are devoted to just design one data structure. And using this, we were able to convert just a lot of data structures to be lock-free. And in fact, for this last one, there's a lock-based construction that was relatively complicated, and there was no lock-free solution until our implementation. And so I'll just very briefly show you the results for the linked list data structure, which all the other results kind of look the same. So this is the experimental results. What we're seeing here is the dotted lines are the lock-based, the blocking versions, and the full lines are lock-free. Okay, and notice that the blue and orange lines, we actually took exactly the lock-based implementations and just plugged in our library to make them lock-free. And the other two were lock-free constructions that were hand-tuned to be very efficient. And what we're seeing here is on the y-axis, we have throughput, so higher is better. And on the x-axis, we have more threads. And so what we see is that the more threads you have in your system, suddenly the lock-based algorithms kind of deteriorate when there are a lot of threads. And with our library, we can avoid that effect. Right? Our library is still slower than the very best hand-tuned versions, but it was quite easy to implement. So it might be a trade-off that you would want to make. So that's it for the experimental results. Yeah. Yeah, there is. So you see the dotted line where the sharp thing happens. So we actually ran this experiment on a machine with 144 threads. So it is possible in concurrent algorithms to spawn more threads than are physically available on the machine. And so that's what we're doing here. And when you do that, what ends up happening is it's way more common that a process takes the lock and then gets descheduled to do something else, which is why the lock-based ones suddenly behave way worse. Yeah, good question. Okay, so that was it for what I wanted to show you about this practical idempotent lock-free locks. And now I just want to point out a theoretical question that arises from this and how we can solve it. So let's look again at our basic construction of how we get this lock freedom. Again, if we have P1 and it wants to grab the lock, it writes down its descriptor and takes the lock. And then if P2 wants the lock, it has to help it, right? But now imagine that we have a scenario where while P2 is helping P1, another process P3 comes along. Okay, and P3 either is faster than P2 and can help P1 faster, or it actually sees that P2 is done helping P1. Well, at this point, it can just take over the lock for itself. Right, and so now, even though P2 already helped someone, right, it can come in and see that the lock has been again taken by someone else, right? And so now P2 has to help this someone else. And this can actually continue forever, right? So P1 maybe now wants to do something new and can take the lock again before P2 has a chance. Right, so the problem here is that a process can be blocked forever, not by slow processes, but actually by fast processes. Right, and it never gets its fair chance at accessing the lock. Right, and so we want to design an access algorithm that will allow everybody a fair chance of getting the lock for themselves. Okay, and so to do that, I want to just very briefly give you some more details on how we model this setting in theory and what the considerations are. So in this setting, we want to grab locks, but the default state, so there's sort of two states that a process can be in. The default one is that the process doesn't currently want to grab the lock. It maybe runs some code that doesn't need locking, and then eventually it gets to a point where it does need the lock. Right, so by default, everyone is this not wanting a lock state. And there are transitions, right? So at some point, some process might say, okay, well, now I want to grab the lock. At that point, it needs to follow the lock protocol, right? And we say that it takes steps. So steps just means that it follows its own algorithm. And we call them steps rather than, I don't know, running time or something like this, because the steps get interleaved with a bunch of other processes' steps. And it's hard to really talk about a notion of time. So instead, we talk about a notion of how many steps did you have to take. So the idea is, while it wants the lock, it follows the lock protocol. Maybe other processes also join and also follow the lock protocol. Eventually, it finishes, and it moves back to this default not wanting the lock state. Now, there are sort of adversaries that we assume are controlling the interleaving between the steps, right? So we assume that there's some oblivious scheduler adversary whose job it is to decide at any point in time of the processes that are actively wanting the lock and executing the lock protocol, who is going to take the next step. Okay, and so basically it controls how the interleaving works. And we assume that it's oblivious usually because these interleavings in practice are affected by things like the caches and the operating system, and they're not actually affected by the values that are being written or anything that's actively going on in the execution itself. So we assume that the scheduler doesn't have access to any of this information. However, there's another adversary, which is the adversary that controls when does a process want to take the lock? When does it sort of enter this protocol step-taking phase? Right, and the reason that this adversary is adaptive is that that is actually controlled quite often by the values that the process has seen during its execution. Right, it might be that if I read something, then it tells me not to grab the lock now, or I read something else and it tells me, okay, you need the lock. Right, so we assume that we have these two adversaries, the oblivious scheduler and the adaptive, we call it the process adversary, where the process decides when to enter the protocol. Okay, so with this setting, remember our question is, can we design some algorithm that ensures fair access while minimizing the number of steps that you need to take? All right, so let's try to design this algorithm and see where challenges might arise. So sort of a very intuitive idea is to say, well, what if I give a random priority to every process, right? And so when I start wanting the lock, want to grab the lock, I'll have some random priority, and if I have the highest priority of everyone else who's competing for the lock, then I win. Right? And this would give me a fair chance of winning as long as the priorities are chosen in a good, independent way. All right. So for that, let's imagine that we have some set of a bunch of descriptors with their priorities. Right? And so if I have P2 and it wants to grab the lock, what it'll do is it will create its descriptor and choose a random priority. And then it will add itself to this set. And then it'll compare, see if its priority is the highest of everyone. And if so, it wins. And otherwise, it will help the winner to make sure that it doesn't have to encounter that winner again if it ends up trying again. Okay. And if you lost, then you can just restart this process, get a new random priority. And if you won, then great. So there's actually a problem with this approach. And the problem is that, remember, the choice of when I actually start this protocol is controlled by an adaptive adversary. And in particular, this adaptive adversary can wait and see what the priorities are of the processes who are already participating. And if it wants to be mean to P2, what it can do is actually wait until it sees that there's someone with a very high priority, and then schedule P2 to start, knowing that there's a lower chance that it will win. There's a fairly low chance that it'll get a random priority that's highest than this very high value. Right, so this is a problem, right? And in fact, an adversary can make P2 do arbitrarily badly. Okay, so we want to fix this. So let's take a look at this algorithm and see what we can do. So the solution that we have is actually quite similar, and the only changes that we make is these green changes. Okay, so the idea is, instead of right away picking your priority, you're going to start the protocol without any priority. Okay, so when you want to grab the lock, you enter the tournament with your descriptor with a blank priority. What you'll do is actually do this helping thing. So you'll check who has the highest priority and you'll help that person complete. And you'll notify the others that they lost and so on before you're even competing, before you have a priority. And so what we get here is that the competitors that were present when P2 joined are no longer present later on when P2 competes by itself. And in the meantime, it's possible that others have joined and maybe they already have their priorities. And eventually, once P2 has cleared all the competitors that were there when it entered, then it chooses its own priority and does the same thing where if it's the highest priority, it wins, and if not, it will try again. Okay, so note the nice thing here is that when the adversary chooses to let P2 enter, it has no information about the priorities that P2 will actually have to compete with, right? All of the priorities that were already there are by processes that will not cause P2 to fail, right? So P2 will help them and clear them from the competition, and only then will it compete. So we weaken the power that the adaptive adversary had over us. Okay, so that's the main intuition. In our paper, we show that this really works. So if you think of K as the maximum number of competitors that we can have at any point in time, we show that this algorithm achieves this lock-free lock property, where it gives everyone a chance of at least 1 over K to succeed at any in any attempt. And each attempt takes about K squared steps.
I don't understand why are you using random priorities here? Can you explain a little bit about that?
Yeah, so the problem is that we need to figure out how to break ties in a reasonable way. And you could say, okay, well, maybe I can queue everybody up, right? And I can just let them succeed sort of in the order that they came in. But intuitively, what that does is it shifts the problem from the lock to the queue. Now the question is, how can I design an algorithm that lets everybody queue in a fair way, right? So because of the concurrency, it's possible that maybe P2 wanted to take the next slot in the queue, but someone else came in and grabbed it, right? And now P2 has to take the spot after that and so on. So we're kind of, we're keeping the same problem, but shifting it. And so it's unclear how you would be able to do this deterministically. And we have reason to believe that it's impossible, but I'll be happy to talk about that offline. Okay, so that's the general result. In our paper, we actually extend this to being able to grab multiple locks at a time. Okay, but that's all I wanted to show you. So I'll just very briefly conclude. So I showed you sort of 2 parts, right? One is we showed that if we have the ability to design idempotent code, then we can have these lock-free locks. And we showed that using this descriptor log, then you can get idempotence in a fairly efficient manner. And then we also have this priority-based algorithms to ensure fair access to the lock, right? And that to get that right, we had to time the priority picking or revealing time to avoid the adversarial effects. And I'll just leave you with a couple of future directions. I showed this idempotence construction and I said it's efficient, and I showed this fair access algorithm, and in the title I said that it's fast, but it's quite possible that we can design better idempotence constructions and a faster fair access algorithm. So that would be very interesting. And the other thing is that we did assume an oblivious scheduler adversary that does have some effects that we had to mitigate in the actual algorithm that I swept under the rug. And I gave you sort of practical motivation for why it makes sense that it would be oblivious. But it's also interesting to ask, well, can we design an algorithm that would work against an adaptive scheduler adversary? And we don't actually have an answer to that. So our algorithm would not work against an adaptive adversary. And with that, I'll thank you for your time.
Maybe one quick question, somebody.
to read the code of one process. It's not creating any overhead, even though you have to do the code of one process multiple times, right? Can you comment a little bit on that? Maybe if that code was very intensive, what would happen?
Yeah, so it is true that, and this goes back to sort of the idempotent construction, right? It's true that if I have many processes competing, it could be that all of them are kind of wasting their time by running the same piece of code. And I think that's an unavoidable part of this concurrency setting, and if we want to have more freedom, it could be a good question of, in practice, can we have some flag that says, you know, if someone finished it, I can raise a flag and then everybody else can stop or something like this. So it does waste some work. And so it's a trade-off, right? In some cases where locks are fine and there isn't too much contention, it might be better to just use a lock that doesn't have everybody repeating the same code. Yeah.
Okay. No.
Last but not least, we'll have Shipra from Google Research, who will be telling us about auctions and advertising. So Shipra did her PhD at Stanford in algorithmic game theory under Tim Rathgarden. So before this talk, actually, we were comparing notes of path, you know, both finishing high school in a foreign country and coming to the US when we were 17, 18 to the undergraduate here and did PhD and end up working for industry research labs. So it's very interesting. So I look forward to your talk.
Thank you. Yeah. So yeah, I was actually a student at Women in Theory the first time it happened, which was in 2008. I was about to start PhD, and I really valued it as an experience at that time. And it sort of gave me exposure to many awesome women from diverse research areas, from theoretical CS. So whenever I went to like Starbucks, Soda, I knew lots of people, which is always a bit daunting when you're a woman. So I appreciate that. It's great that, you know, all this thing has kept going for so many years. So today I'm going to talk about simple mechanisms for rich advertising auctions. This is joint work with Gagan, Aggarwal, and Arnab Mehta from Google, and Alex Somas from Purdue, and Divyarthi Mohan from Tel Aviv University. You've seen this screenshot in Gagan's talk, but so the sponsored search auctions, which are auctions for ads that are shown next to your search results on, say, Google or Bing, they look very different now than they used to 10 years ago. So 10 years ago, these were just position auctions for text ads. So each ad was just a headline, URL, and 3 lines of text. All ads were of the same height. And every advertiser used to provide only a single ad. So it was a simple, just like select the top K problem. But nowadays, we have the flexibility to show bigger or smaller ads with different amounts of details. So the same advertiser might provide multiple ads, and then we are trying to find the best set of ads to show. And to sort of illustrate this point further, here's sort of a sample of different kinds of ads that can show up for a query like rental cars. I know the text is a bit small to read, but like they're just ads from different advertisers. And you can kind of also see the kinds of details they have. They might have site links taking you deeper within the website. There might be a link to download their app. There might be a rating that telling you how reliable the merchant is. There can be offers to kind of convince you to click on their ads. So all of these details affect the probability of click for that ad. It also affects the amount of space this ad takes up on the page. But we still have the limited amount of space in which we can show ads because we don't want to overwhelm the user with ads. So then we encounter a packing problem. So what is the best set of ads that we can show in this space? And for sort of like this economic setting, we are going for this talk in particular, we are going to focus on social welfare as the objective to measure how good a set of ads is. And in the sponsored search auction setting, advertisers normally specify a value per click, and then the probability of a click on the ad can be learned using a machine learning model. So the social welfare is sum overall advertisers of their value per click times the probability of click, which is kind of like the total value that everybody gets out of the allocation. And then we have constraints. We have a knapsack constraint that says that the ads must fit within the available space. And we're only allowed to show one ad per advertiser because it wouldn't give users good value if we were repeating the same ad from Expedia twice with slightly different formats. But there is additional complexity. The inputs to this algorithm are provided by strategic agents, which are the advertisers. So advertisers might have their own intrinsic value per click, and then the set of rich ads that they want to show, which is kind of like what are they trying to market to the users at any given point. But if we don't design our auction carefully, they might misreport some of this. They might report a different bid or only report a subset of the ads to kind of make sure that we give them exactly what they want and nothing else. And in particular, we'll assume that the advertisers have quasi-linear utility. So they're trying to maximize their value minus the cost. And in the sponsored search setting, the cost is usually represented as the cost per click. So the utility is probability of clicks times or expected clicks times value minus the cost per click. And as I said, the advertisers would misreport their bids and rich ads to maximize this utility. So we want to design a truthful auction, which gives us a guarantee that the advertiser will maximize their utility if they just give us their true preferences. They'll report their true value and set of rich ads. And this is a dominant strategy for them. So no matter what anybody else is doing, they can just report their true value and be assured that this will give them the best utility. The main result in our theorem is in our paper is we provide a truthful auction that provides a 3 approximation to the optimal social welfare. And the benchmark that we're competing here is optimal social welfare assuming truthful reporting. And in fact, actually, we are competing against the fractional optimal, which I'll talk about more later. And there are 2 reasons for approximation here. One is computational, because the problem is NP hard. And then second is truthfulness, to align sort of the advertiser's expectations with what the auctioneer wants to maximize. We have to also give up a little bit on the approximation. The area of rich ads is actually very rich, and sort of as internet advertising has evolved, various teams have come up with different models that capture some aspect of it. And so there's a bunch of works from different industry groups related to this. The first couple are actually looking at sort of the computational problem where we can't solve the optimal problem. How should we approximate it? What kind of incentive and approximation guarantees can we provide? And then the second group is actually dealing with this property. So rich ads is actually a special case of combinatorial auctions, which is a much more general model. And in combinatorial auctions, classic auctions like VCG and all do not provide core allocations, which kind of basically means that we could add more competition to an auction and make less revenue, which is a very counterintuitive and hopefully wouldn't happen, but can happen. So the latter two papers are trying to deal with that while sort of assuming good computation is available and things like that. But those are definitely a couple of interesting research agendas in this area. So now let's dive into sort of the technical details of what is our algorithm and how do we do it. So let's first understand the benchmark, which is the optimal social welfare without incentives. So we can write it as an integer program, relax it to an IP, and it's a fairly simple program. We have a knapsack constraint, and then we have these additional constraints of only one ad per advertiser. This problem is actually NP hard. This is not surprising because it's knapsack plus added constraints. But just like so the main difference from knapsack is, so we have items which have value and size, but they're grouped together. And then we have a constraint that within each group, we're only allowed to pick one item from each group. And so that gives a slightly different allocation than we would if we didn't have this group constraint. But just like in the case of knapsack, even this problem we can solve using a simple, so even the fractional optimization of this problem, we can solve using a simple greedy algorithm. So this is a result by Sinha and Zoltners from '76. We actually proved it ourselves and realized too late that it was already well known. So there is a lesson there of like doing your literature search. But so the idea is that we should allocate in the incremental bank per buck order. So for knapsack, normally we allocate in the bank per buck order. Here, because we have a constraint of only one ad or item per group, whenever we add another item from that group, we have to remove the previous one. So we have to consider sort of what is the incremental value of adding this item divided by the incremental space that it will take. So in that sense, like if all the items were very well sorted in terms of value and size, then you could just reduce this to knapsack and then solve the knapsack problem. In reality, they might not be well sorted. There can be other items which are higher value, lower size, and things like that. But those will be dominated. The optimal solution won't use them. And so then sort of the first step for the reduction is just saying like there are these items which the optimal solution won't use. Let's get rid of them. And now we can reduce it to knapsack. And so that gives us the fractional optimal. Here, I also have an example to just illustrate what this incremental bank per buck means. So for the first item from a group, there's nothing that has been placed before. So the incremental bank per buck is just the bank per buck. For any subsequent item, we compute the incremental bank per buck as sort of the incremental value over the previously placed item divided by the incremental size. So you can think of it as just taking the large item and breaking it up into two smaller pieces and sort of thinking of them individually. And when there are multiple items in a group, we sort of do it consecutively. So any two consecutive values will sort of consider the incremental piece for each subsequent one. And so here's sort of a sample run of the incremental bank per buck algorithm. And so it will just keep adding items. And whenever the next item in the incremental bank per buck is from a group that's already placed, like the 18 and 21 value one gray items here, then we'll just replace the previous one. And then finally, we'll get to a stage where the next item that we want to place is too big for the remaining space available. So that's where we add it fractionally. But we won't just add this item fractionally, but we will steal space from a previous item from the same group. So like in this example, the 21 value item was already added. We take a little bit of space from the 21 and give it to this 30 item to sort of optimize within the available space between these two items that are available. But the nice thing about this is that the optimal fractional solution is mostly integer, except for this one group where there are two items that we are fractionally allocating in between. Every other item is allocated integrally. And this also gives us a two approximation algorithm, which is also similar to like what we have for knapsack. So if we just take the allocation before we added the last item and the last item, and then pick the larger of these two, that actually covers the fractional solution. And so it gives us a two approximation. So there is a simple two approximation algorithm for multi-choice knapsack. But this was without any kind of auction design consideration. So now let's go back to a truthful mechanism. how are we going to do that? There are two common truthful hammers that are used in algorithmic game theory. One is the Vickrey-Clark growth mechanism, other is Meyerson's lemma. So which of these can we use? The Vickrey-Clark growth mechanism is a really strong result, pretty awesome. It's pretty general. It can be used in multi-parameter settings. And all it says is that you should solve the optimal problem and then charge to each advertiser or each participant in the winning solution their externality, sort of what damage are they doing to everybody else. And that externality can be calculated by just solving the optimization problem without this participant, and then subtracting from that what everybody else is getting in the optimal allocation. So it's sort of very simple and very clean. And this is truthful, and the truthfulness sort of follows from the fact that we are solving the optimization problem optimally. So it kind of aligns the advertisers' incentives with the auctioneer's incentives. But it's not computationally feasible. It requires us to solve the computational problem n+1 times, basically. And there are some extensions. So this is sort of a common problem that's encountered in combinatorial auctions in general. And there are some extensions in some special cases where we can still use this template with an approximation algorithm to provide a truthful auction, but it's not sort of a general hammer in that sense. Closing the doors. Yeah. So basically, like, we don't know how to do this in this setting. Question.
Yeah, just a clarification question. So, so there are settings where this mechanism can also be read. So it's very simple. So is anything like that we use in combinatorial, or is it like too complicated?
Yeah, it's too complicated. It doesn't become as simple from the second price for any size. Actually, even sort of like just a simple sponsored search auction setting, like the position auction setting.
Yeah.
If like the second price, like the truthful payment rule is no longer simple. In fact, there we kind of say like, oh, actually, it's not too bad because like the Meyerson interpretation would be hard, but look at the VCT interpretation; it's so easy. But it's out of reducers. Like, this is the simplest we can describe VCT as, like, solve the optimal problem n+1 times basically. So the second hammer is Meyerson's lemma. So this is a very classic and awesome result by Meyerson, which says that in a single parameter setting, so if every participant is just giving us one value, then a truthful auction is equivalent to having a monotone allocation rule. So if somebody bids higher, they get allocated more. And then that can be paired with a unique payment rule, which is just some integral based on sort of the allocation rule. And that auction is truthful. And sort of the payment rule actually also has a nice interpretation that also gives us like some like pictorial proofs of why this is truthful. So the payment is just this area above the curve for the allocation. So in the picture here, the curve is sort of showing the allocation rule. So as the advertiser or as a participant raises their bid, they'll get more and more. And the payment is this area above the curve that's shaded. But this is for single parameter. So what we do here, what we're trying to do here is actually still use the same formula, but not, like, it doesn't follow directly from the lemma, but we can follow the same steps. So we will try to design an algorithm that is monotone in value per click and a set of rich ads. And in the case of set of rich ads, it's a set. So it's more of like a set, like if you give a subset of ads, you get less. If you get a superset of ads, you get more kind of monotonicity. And then we can pair it with Meyerson's like payment rule and prove that the resulting auction would be truthful. And so there's like a small lemma here to prove that like this combination works out. And this is similar to what has been done in recent years in some of these 1.5 dimensional revenue maximization papers, where they similarly have a multi-parameter setting with multiple dimensions being controlled, but one of the dimension is non-monetary. And then they prove similar results saying like, let's give a monotone allocation rule, pair it with Meyerson like payment rule, and that becomes truthful. That reduces our problem to just designing monotone allocation algorithms. And so we have to prove that the participant won't be able to gain more by sort of reporting a lower value or reporting a subset of ads individually. We don't have to do the together part. The together part is already done in the lemma. So what is a good monotone algorithm? So we find that a lot of the standard algorithms we might use in this allocation are not monotone. So one is just like comparing set of ads. So maybe we somehow come up with like some different ways of putting the ads together. And now let's just compare the two and pick whichever is the higher. Turns out that's not monotone. So in this simple example, where this is the universe of ads, if the gray advertiser removes the smaller ad, that's going to force our algorithm to pick this larger ad, this larger single ad. And so they can get higher, bigger allocation by reporting a subset of their ads. And in fact, the same example also shows that the integer opt, if it was somehow computationally tractable, is not monotone, because that's exactly what we're doing in integer opt. Then the second thing is maybe the incremental bang per buck algorithm that we use for the approximating the fractional opt, maybe that is monotone. Turns out that's also not monotone. So the allocation on the right is sort of what you get if everybody's reporting truthfully. Now let's suppose that the blue advertiser removes their smaller ad. Now their bigger ad, which earlier had small incremental bang per buck, now we just consider the bang per buck for it, which is higher. So it gets to be allocated sooner. And so in the resulting allocation, the blue advertiser gets a bigger ad and more allocation, so they're better off. So that doesn't work. But not all, yeah.
So advertisers just want to have more space. That's it?
Yeah, so more space, well, so there can be, like, I guess we're considering the general model where more space may not always mean more click-through rate.
Yeah.
So what they really want is more click-through rate.
Okay.
But if there were things where like more space does not mean more click-through rate, then we should just remove those, like not allocate those.
Okay. So they don't want to maximize their backward.
No, yeah, they want to just maximize their value, which is the value for a click times click-through rate, which is sort of like the numbers written here are just those like the combined quantity. So here's a simple algorithm, which is monotone. Just allocate to the highest value. If there is space remaining, keep going. That is clearly monotone. Like bid higher, you get more. If you remove something, it doesn't matter because whatever, like the highest value one that you are getting, that's still there. The problem is this can lead to very poor approximation. There might just be a massive ad which just happens to have a lot of value. We place that, it blocks all the space, nothing else can be packed. And this can be like infinitely bad in the worst case. There's another algorithm, which is monotone, which is to allocate in the bang per buck order. So this is like the algorithm we had for knapsack. It makes a comeback and it is monotone. So sort of the high level intuitive idea is the bang per buck order is kind of independent of what else is present. Like if you remove some subset of your ads, doesn't matter, the rest of the ads are unaffected. There is a little bit of caveat there, which is that the bang per buck order is kind of not absolute. Sometimes there might be a lower bang per buck ad, which is also lower value, in which case we don't want to allocate it. So there is a little bit of care required in the proof to kind of think about all the possible cases and argue that in each of those cases, nobody will be able to gain by reporting a subset of their ads. But it can be done. We can prove that this is monotone. And so here's like a sample run of the bang per buck algorithm, where now, so the gray ad gets a much bigger allocation in the bang per buck order. And we end up stopping early because the next ad that we would have considered in this order, which will be the pink ad, cannot fit within the remaining space. So already in this picture, it looks like it's not as good as the sort of the fractional opt or the integer opt we could come up with, but maybe it's a good approximation. Turns out still not. You can consider a very bad example. Like if you have seen the bad example for knapsack where bang per buck fails, it's similar. The same example works. So of course, this is not by itself is not good, but maybe some combination of the bang per buck and highest value that could work. So that's a theorem that we proved, that allocating in the bank per book order with probability 2/3 and picking a single highest add with probability 1/3 will give us a tree approximation to the fractional opt, and it will also be monotone. Note here that we are randomizing between those two allocations. We are not picking the higher of the two, which is kind of what we do for the approximation algorithm. And that's mainly to preserve monotonicity, because again, otherwise that will, like as I showed in the example, it breaks. And interestingly, this is another approximation algorithm for multi-choice knapsack. It's slightly worse than the two approximation I proved earlier. But like from a practical perspective, it's kind of nice. Like if you didn't know about multi-choice knapsack, you just use the knapsack algorithm, you wouldn't be too worse off. And this analysis is tight. There we have an example where you cannot do better than a 3 approximation in that example with this construction. Thanks. All right. So then we have a monotone allocation rule. It can be paired with Meyerson's like payment rules, and we'll get a truthful auction. Now let's switch gears slightly and talk about GSP. So in the sponsored search setting, due to various historical reasons, we don't implement the truthful auction like VCG or Meyerson's like payment rules. And the story was kind of very simple. We know for a single item, second price is truthful. So then when they were going to multiple slots, they just said like, let's continue second price. And it took a paper by Gagan actually to show that, no, that's not truthful anymore. And Halavarian also had a similar paper around the same time. But the main difference for GSP compared to Meyerson is that when you have like a step function allocation, where as you bid higher, you get higher on the page or get bigger and bigger allocation, Meyerson says we should charge the area under the curve. So sort of like for each step in click-through rate, like charge a high price only for those incremental clicks, while GSP says, let's charge the high price to all of your clicks. And that creates, so we are charging a lot more than we would with the truthful payment rule. And that creates an incentive for the participants to lower their bid to get a better trade-off between the value they're getting and the cost they are paying. So GSP is not truthful. And even in this rich ad setting, where now we have a monotone allocation rule, so we could sort of define a similar payment rule, which is just sort of like, let's find a threshold where you start losing clicks. That is also not going to be truthful. So what can we say about sort of the social welfare that we get in this? Well, we can use price of anarchy. So price of anarchy is a very nice solution concept introduced in like one of the major contributions of the algorithmic game theory community, introduced by Koutsoupias and Papadimitriou in 1999. And it has been studied in various models like condition games, auctions, social networks. So it's like a popular metric for us. So what we do is, because the auction is not truthful, we can't just focus on the settings where everybody's just bidding their true value. So we look at a Nash equilibrium where everybody's still maximizing their utility, assuming everybody else is just bidding whatever they're bidding. So I want to best respond to whatever everybody else is doing. There can be many such Nash equilibria. So to measure the price of anarchy, I want to look at the worst case. So what is the worst case approximation a Nash equilibrium can have compared to the social optimal? And the same metric can be extended to more general equilibrium concepts like mixed, correlated, or Bayes Nash. And Bayes Nash in particular is or perhaps the more relevant one in an auction setting, because the participants have values drawn from distribution, and the Bayes Nash kind of captures that. So we proved that the pure Nash price of anarchy in this setting is about 6. So we are still doing like the bank per buck allocation, pairing it with GSP payment, the highest value allocation, pairing it with GSP payment. We're picking between these two with some probability. We use it half-half here instead of the 2/3, 1/3 before. And we show that this has a price of anarchy of 6. And this can be extended to more general solution concept like mixed and Bayes Nash using smoothness, which is this general hammer that was proposed by Ravkardin and extended by Sirkanis and Tardosh to various settings. And our proof in particular follows a template from Karagianis et al., where they proved price of anarchy bounds for the GSP auction in the position auction setting. And so sort of like once you have the pure price of anarchy proof, with the smoothness framework, you can easily extend it to more general solution concepts. So There's lots of interesting open questions that can be solved in this Richard advertising auctions domain. There's definitely open questions related to some of the related works I cited earlier. For the model in particular that we study, I think in terms of designing truthful auctions, we're just getting started. In real world auctions, we have position effects. So if your ad is shown higher on the page, you will get a higher click-through rate, and our model right now is not capturing that. There is usually also a number of ads constraints, like we want to only show 4 ads, and we are not capturing that right now. And then the second thing is like how to maximize revenue in this setting is also not well understood. Because now the advertisers are specifying a value per click and a set of ads, this is no longer a single parameter domain. So we cannot use all the standard machinery. It might not be as hard as sort of like some of the like 2-item combinatorial auctions kind of settings that have been studying, which have proven hard. So it's something more like the 1.5 dimensional setting perhaps, but there's still work to be done to figure out the details of it. And thank you. And we have our paper on archive if anybody wants to look at it.
Yeah.
So you mentioned that the algorithm, the one that shows bytes analysis, but is the problem generally hardly strongly NPR? I mean, is there a PTAS for it?
Yes, there is a PTAS for it. So like knapsack has a PTAS. I think we can develop a similar PTAS unit for this. That won't be monotone. We don't know how to make it monotone. Right, so there will still be a question of how to design a truthful auction.
Also, the other thing is, so you mentioned the setting is where each advertiser has a bunch of options that they take. If you remove this constraint, is it going to make a problem here?
Yes. So if each advertiser just has a single ad,
yeah,
but it can be of different sizes, yeah, then it doesn't become a multi-parameter problem anymore. It will still be computationally hard. But I think in that case, we could use a PTAS because like the monotonicity is harder because of this set function. Like getting monotonicity in the bid is fairly easy.
Is there a lower bound node for the same thing? Like you have a 3 approximation with it there.
Yeah, no, actually don't know the bound. Yeah. I think like, so there's like this VCG angle for designing truthful auctions. So right there itself, maybe something could be done, but we don't know how to do it. And then even within Myerson, maybe there's other ways of approaching.
One more question. So what I understand is you're assuming that it doesn't matter like where the ads are placed, like as long as it's there. But if there's a submodular, like if there's a diminishing value to where you position the ad, and then maybe there's no limit, but something like a diminishing value, would that make the problem?
Yes, yeah. So so the position multipliers is kind of capturing that, right? So you could say like there is K, but like there's an exponential drop off. Like if you have a K tag shown, then you have like exponentially lower but position multiplier. So that would be one model, and we don't know how to solve that. Another actually interesting aspect is that even the position multipliers might not be the right. So what matters for your click-through rate might not be how many ads are about you, but how much space is occupied about you. So your click-through rate should be a function of how much space is occupied about you and your size. And yeah, we don't know how to solve that.
All right, so let's thank Shifra again.
We can't hear you.
So in the schedule, you might remember that we had planned for a 30-minute industry panel, but we're not going to have it anymore because when we planned it, we didn't know the industry speakers would be with us for the main panel yesterday. So this actually is the end of the sort of the intellectual part of the workshop. And the last organized event is lunch outside. And after that, we are done. And then I know you all have travel plans and all that. So safe travel home. And we should stay in touch with email. We want to post everybody's emails, hopefully, a long-term email, not the one that you have with your current institution, so we can all stay in touch, etc. So do let me know personally if you have comments, concerns, suggestions. You can put it in the survey. It's completely anonymous. We don't know who writes it, who wrote it. So, but it's so wonderful to have you here. It's my first event since pandemic. So, it's really wonderful. So enjoy the lunch. It's awesome. Shivangi is not here either. So we're thinking, so with all the help and you girls are so wonderful, next time perhaps we can have a workshop without any organized present. So you can just do it all by yourself. Yeah.